In this next PowerPoint presentation, I'm going to go over what frequency distributions are. And frequency distributions also include how to display the data. So this could be histograms, bar charts, and polygons. Okay, so let's talk about proportions first. Proportions is just another term for relative frequency. So what this is going to do, you're going to try to measure the fraction of the total group that's associated with each score. Okay, so proportion, will slanted P there, equals frequency, or F, divided by N. And again, big N is the total number of people in your study, or the total number of scores for that population. It's also called relative frequency because they describe the frequency in relation to the total number of people in your study. Okay, so what do we include in a frequency distribution table? You look over here in the far left-hand side and you see raw scores. Again, raw scores is noted by an X. So we're going to say these are, pop score quizzes, right? I never give pop or pop quizzes scores. I've never given a pop quiz, but if I was, it would be short ones. So we're going to say the total number of questions you can get right is 5. And so we would say, okay, well, how many people in this class that I gave it to scored a score of 5? And over here under the F column, or the frequency column, I can see that 2 people scored a score of 5. So to find out the total number of people in my study, I would go 2 plus 3 plus 4 plus 1, so I would have 10. So the number of people that scored a 5 would be 2 out of 10, or 2 divided by 10. So the proportion is always in a decimal, so 0.2, and all I do to convert that to a percentage is multiply it by 100. And so I multiply 0.2 by 100 and I get 20%, or in other words, 20% of the people in this class that I gave a pop quiz to scored a perfect score of 5. Okay, going down to the next one. So how many people scored a score of 4? Well, 3 people. So 3 divided by 10, or 3 out of 10 total number of people, gives me a proportion of 0.3, or 30%. And I keep doing that for each one of the scores possible. So 3, I had 4 people do that, so 4 divided by 10 would be 40%. And these decimals here should add up to 1. And I say 1.999 was okay, depending on how many decimals you pull your number out. These are pretty easy round numbers, so mine's going to add up to 1. And then out of our percentages, it should add up to 100%. So I'm going to keep doing that. For each one of the possible scores, I have 2 left and 1 left, and looks like nobody scored a 0, so that's good. Okay, so what it looks like now is here, and you can tell the 0.2, 0.3, 0.4, 0.1 add up to 1, and my 20%, 30%, 40%, 10% add up to 100%. Okay, let's take a look at this one. Okay, it says use the frequency distribution table to determine how many subjects were in this study. Again, over here we have our X's, these are our raw scores. And over here is under the frequency table, or under the frequency column, is how many people had that score. So we had 2 people score 5, we had 4 people score 4, 1 person score 3, right? And so to find out how many people are in your study, you add up all the F's, or all the frequencies. Did you get 10? Hopefully. Okay, how about this one? True or false? More than 50% of the individuals scored above 3. Let's take a look at the frequencies of each of the different scores. What do you think? Do you think more than 50% of the individuals scored above a 3? They did, 60%, or 2 plus 4, right? Because I had 2 people score a 5 and 4 people score a 4, so that's 6. That's out of 10, right? So 2, 4, 10, 60%. So yes, true. Okay, what about this one? The proportion of scores in the lowest category is P equals 3. So it's kind of a tricky question. Proportion, again, is always in a decimal, so it should be 0.3. Right? Proportion is always in a decimal, and percentage is always in a percentage. Okay, histograms and polygons. These are used for any kind of data that we're trying to observe or measure on either an interval or ratio scale. So think back to your scales of measurement, your nominal, ordinal, interval, ratio. Right? So if we're going to display data in either a histogram or a polygon, we need to make sure that our data is either an interval or ratio scale. They're going to always have 2 axes. The y-axis has categories, right? And it's going to be from left to right increasing. And the y-axis has frequencies, and these are going to be from the top to the bottom increasing. Right? So it's always going to meet at the bottom left-hand corner at the 0. Okay. When we create a histogram, we're going to list all numerical scores on the x-axis, the down below one, the horizontal one. You're going to include those even with a frequency of 0. So even if I didn't have a person who scored a 3 out of 5, right? I still need to put 3 there to make my histogram consistent. I'm going to draw bars above each of the class intervals, and the height of the bar corresponds to the frequency. The width of the bar corresponds with the real limits. Okay, so let's talk about real limits for a second. For continuous variables, right? So height, weight, age, salary, debt, anything that can be continually broken down to smaller and smaller units, the score recorded corresponds to an interval or a range on the number line rather than a single definite point. Right? So say I'm looking at the height of the students in the class, right? And I would say, well, if you're around 5 foot tall here, around 5'2" here, and my 5'4" people over there, my 5'6" people over here, right? Individuals with the same recorded score might have different measurements, right? So I might be in the 5 foot tall range, but if I don't give a 5'1" or a 5'1/2" inch, if you're 5'1/2", you'd have to be in my range versus like a 5'4". Right? So we're going to have the same recorded score, but maybe have slightly different measurements. For a group frequency distribution, the apparent limits are smaller than the real limits. Right? An interval extends from the lower real limit of the lowest score to the upper real limit of the highest score. So let me just kind of show you on the next slide here what I mean with that. Okay, so take a look at this. First question, what's the apparent limits for the score of 73? Right, so say you're measuring grades on a midterm exam, right? And so we'd say, okay, what's the apparent limits for a score of 73? Well, if we break it down, we say, well, between 72 and 75. In this case, 5 people scored that. Now, with the real limits, though, 73 gets a little bit trickier. The real limits is 71.5 all the way up to 75.5. Think about it like in your like a grade. So say this was your midterm exam and you scored a 69.67. What would you say that was? A D or a C? Like if I had everybody line up at the back of the class and say, I want all my A's over here, all my B's over here, all my C's over here, all my D's over here, right? And just kind of keep saying all the different grades. Well, if you got a 69.67, that's basically a 70, right? It's super close because you round up. That's what this premise is here too. Or if this was like your final exam, if your final grade for the class, and you ended the class with an 89.9, what do you absolutely know you're going to get on the transcripts? You're going to get the A, right? Because I know how to round up, and an 89.9 is in that same real limit category of the A range. Okay. So group frequency distribution has categories 0 to 9, 10 to 19, 20 to 29, and 30 to 39. What's the width of the interval 20 to 29? How many possible scores can you have in there, right? Or what's the point spread, if you will, right? 20 to 29. Now, at first blush, it almost looks like 9 points, right? Because we take 29 and minus 20, that's 9. That's not true, though, because you could score a score of 20, right? Okay, so the way I was taught to find interval widths is you take the 29 and you minus the 20 and then you add a 1, basically. With this method here, you're adding 0.5 on each side, right? So the real limit of 20 to 29 is really 29.5 all the way down to 19.5, where you'd have a 10-point spread. Okay. This is what a histogram looks like. This is a simple frequency distribution, meaning that all the scores down here have a place. Okay, so again, this is our pop quiz example. So you could score a 4 out of 5, a 3 out of 5, a 1 out of 5. Right? The raw scores are on this x-axis. Okay, the frequency is on the y-axis. Right, so I had one person score a score of 1. I had 4 people score a score of 3. Okay, so this is what the numbers, the data looks like numerically. A histogram allows us to look at this data graphically. Okay, again, this is a simple frequency distribution histogram. Okay. This right here is a grouped frequency distribution histogram. Or in this chart, I'm grouping together certain numbers. Right? Look over here how I have it displayed numerically. So if you had a score between 30 and 31, and 2 people raised their hand and said, yep, that's me. Or a score between 32 and 33, and 4 people raised their hand and said, that's me. Right? Let's find one. Let's find 38 to 39. So we have 38 to 39 here. 6 people that said they had either a score of 38 or 39. Now, a grouped frequency distribution table is good because it's not as cluttered as a simple frequency distribution. Because if I had to include a place for each and every individual score, this x-axis here would be twice as long. Right? So I would have to have one for 38, one for 39, one for 40, one for 41. But with grouping it makes it more concise. One of the drawbacks, though, with group frequency distribution displays is that you lose some data. Okay, so let's go back to this 38 to 39, this green bar here. Now, 6 people raised their hand and they said that they had a child who had a height of 38 to 39 inches. Now, could all 6 of those students or all 6 of those children have a height of 39 inches and nobody has a height of 38? Yep. Could we have 3 children at 38 inches and 3 children with 39 inches? Yep. So one of the drawbacks is that you start losing some of that precise data when you start grouping frequency distributions in histogram. Okay, so again, you're going to list all numeric scores on the x-axis. You're also, and this is really important, you have to include those with a frequency of 0. Okay, so I'm going to go back up one slide. So with this one, I don't know, let's pick on 36 to 37. Say I had no children that said they had height between 36 and 37. This orange bar would then go away, but I would still have to give it a placeholder down here. Now, it not having a colored bar right there would denote to me that the frequency is 0. Okay. Okay, polygons. So same thing, like a histogram, you're going to list all the scores numerically on the x-axis, including those with a score of 0 or a frequency of 0. You're going to draw a dot, though, above each of the center of the interval. Okay, and again, the height of the bar corresponds to the frequency. This time, though, with all those dots, you're going to start connecting them with one continuous line. And you always close your Y with a 0 point. Polygons can be used with group frequency. They just look a little bit different, too. So the first one we're going to look at is a simple frequency distribution polygon. Okay, again, over here we have the display numerically, and in the center here we have it displayed graphically. So we have, I don't know, let's pick on a score of 3. Okay. So we had 4 people that had a score of 3. Okay. You see how the dot is exactly over the 3? Right? What that means, or what that symbolizes when the dot is exactly over the score, is that this is a simple frequency distribution polygon. You see where at the 7, we don't have anybody that scored a 7. 7 is 0. You see how they closed it, though? So you don't leave it just kind of hanging right there. You have to close it with a 0. Now take a look at the next slide. Watch what happens to the dots and their placement over the numbers. See how they're in between now? When a dot is placed in between the scores or the x-axis numbers, then implies a grouped frequency distribution polygon. Okay. Or in this case, right, we had a score between like 4 and 5. We had 2 people that had that, and again, Over here, the frequency, this is up and down the y-axis, 2. So we had 2 people that scored between a 4 and a 5. So I'm going to place that first dot right in between my 4 and my 5. And I'm going to do that for each one of my groups. So between 6 and 7, between 8 and 9, right? I'm going to keep going through that. And again, I'm still going to close it at the 0. Okay. So that was interval and ratio. But what about nominal and ordinal data? How do we display that? Well, for non-numerical values, we use a bar graph, right? It's similar to a histogram, but the main difference between a histogram and a bar graph, you're going to have space, right, between the bars. And again, this is good to use for any kind of nominal, right, so names or categories, or ordinal, rank data. Okay, so we have 3 different personality types here. We have A-type personality, B-type personality, and C-type personality. See how there's a gap in between each one of those personalities? This is displaying discrete variables, right? You can't have an AB personality or a AC personality. If you take a personality test, it's going to tell you either have an A-type personality, a B-type personality, or a C-type personality. The same thing happens here though with frequencies, right? So we know we have 10 people that have an A-type personality, only 5 people with a B-type personality. So this y-axis, this up and down or vertical axis, is still our frequency, and our horizontal, sideways or x-axis, is our scores or types. Okay. When the population is small, scores for each members are used to make a histogram. Right? But when the population is large, scores for each member is not possible. Okay? So what we start doing is we start using graphs based on relative frequencies. And graphs are just a really fancy term for smooth curves, and their purpose is to indicate exact scores were not used, right? So like with a polygon, you're going to have like a jagged straight line, straight line, straight line, straight line. With a curve or a graph, you want the smoothness because what that's saying is it's not exact. Right? The exact scores weren't used. Maybe some of you have heard of like a bell-shaped curve or a normal curve, right? This is any kind of curve where the symmetry, the greatest frequency, right, is in the middle. And it's the common structure and data for many of our variables that we deal with in statistics. Okay, so take a look at this distribution, right? So it's a traditional normal bell-shaped curve. Keep in mind what you know about frequency, right? So the higher the point is, the greater the frequency. Right? Just take a look at this distribution, and without really knowing a lot about distributions yet, can you see what the average IQ for people is here? You see how you have some people, right? Again, this is frequency, right? So you have some people that have an IQ in the 70s, and it's starting a little bit higher. We have more people in the 80s and 90s. But the average IQ, right, where the bulk of our distribution, our population piles up, is around 100. And then it starts to taper off again. You're going to have some people in the 110s, right? And in the teens, and in the 20s, and in the 30s. And these do keep going on and on, right? But the bulk or the majority of the people have an IQ score around 100. A couple different types of symmetrical distributions. In this first one, you have a unimodal distribution. So uni meaning one, where you have one peak, right, and it tapers off again. This is called a bimodal distribution. Right? You can have a tri or a quad modal distribution. It just means that, again, if you cut the distribution right in half, this left-hand side looks like this right-hand side. Right? Same thing over here. The left-hand side looks like the right-hand side. Or if you took a piece of paper and you fold it in half, right? Both sides of a symmetrical distribution will match when you fold that piece of paper in half. Okay, so you have symmetrical distributions, and then you also have skewed distributions. Okay, so again, this is the frequency, and this is the score. With a positively skewed distribution, your bulk of your data is going to pile up on this left-hand side, and then it's going to taper off, and the tail is going to point towards the positive end of the number line. With a negative distribution, the bulk of your data is going to pile up on the right-hand side of the distribution, and then taper off, and the tail is going to point towards the negative end of a distribution. Now, really important, positive doesn't necessarily mean good, and negative doesn't necessarily mean bad, although they can, right? Think like, I don't know, amount of student loan debt, right? So we use the exact same variable for both. So over here is frequency, right? And this is 0 right here. And as we travel this way, the numbers get larger and larger and larger. So say over here we have like $10,000 in student loan debt and $20,000 and $30,000 and $40,000. And over here is like, oh, like $70,000, right? So it's actually good if this is student loan debt to have a positively skewed, because the bulk of the data is going to pile up on this left-hand side. And again, it's called positively skewed because this tail, this little bitty part right here, points towards the positive end of the number line. Okay, now let's look at if it was a negatively skewed distribution. So again, student loan debt, frequencies go up higher, 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 and then debt ratio goes higher, higher, higher this way. So with a negatively skewed distribution, you have the debt, right? Only a little bit of people have, loans over here, and then the loans get bigger. So 20,000, 30,000, 40,000. Oh my goodness, look at this. The bulk of the people have $60,000 or $70,000 in student loan debt. Right? So over here we have a positively skewed distribution, which is good, right? Meaning that most people don't have that much debt. Over here we have a negatively skewed distribution where it's bad. Right? But again, it doesn't always mean positive, it doesn't always mean negative. I have videos that I have made that shows when these are good and bad. Okay. Researchers describe distribution shape in words rather than drawing it. So you're going to call it either symmetrical distribution, right, or a skew distribution. And you'll start reading in literature, right, it had a negatively skewed distribution or a positively skewed distribution. It just means that in the skew distribution, researchers didn't necessarily do something wrong. Just for whatever reason, the scores are piling up on one side and tapering off in that tail on the other. And it can be either positively skewed or negatively skewed. Okay, so just take a second and draw a couple, right? It's not too hard. You just kind of make a little bell-shaped curve or a negatively skewed distribution or positively skewed distribution. Just take a couple seconds and draw a couple. Okay, so learning check. What's the shape of this distribution? Okay, so you have to ask yourself, okay, where's the body? And which way is the tail pointing? Okay, positively skewed. Or in other words, the bulk of the data piles up here and tapers off, going towards the positive end of the number line. Okay, think about this one. A treatment center for children measure the marital status of their parents, single, married, divorced. A histogram would be appropriate for this type of data? True or false? What do you think? False. Marital status is a nominal variable, right? So in this case, a bar graph is needed. You can't be both married and separated, right? Or I guess you get married and divorced, right? You can't be never married and divorced 3 times, right? So you have to, you can't be divorce-ish, right? You're either divorced or not divorced. So a marital status is a nominal variable. So in this case, a bar graph. Okay, what about this one? A treatment center for children measured the time they spent playing with other children in minutes. A histogram would be most appropriate for this data. So think, what kind of data is time? Is time a continuous variable or a discrete variable? Right, time is continuous. It's a ratio, right? For nominal ordinal interval ratio, be more ratio. And so you need to use a histogram.